I'll be talking on behalf of the TOROS collaboration, and I would like to talk about what is this project and what are we doing. TOROS is an acronym for Transient Optical Robotic Observatory of the South, and it's a planned observatory to be in the southern hemisphere in Argentina. It's a site where very good seeing conditions, and the particularity is it's going to be an observatory dedicated almost completely to respond to advanced LIGO and advanced Virgo trigger alerts. These two, advanced LIGO and advanced Virgo, are gravitational wave detectors. And the goal of this TOROS project is to identify the optical counterparts to those gravitational wave events. Gravitational waves are, you probably heard, ripples in space-time predicted by the Einstein's general relativity theory. And these ripples go in travel in space and are detected by these huge kilometer-wide interferometers. We have two in the United States that comprises LIGO, and then one in Europe for advanced Virgo. And they, by measuring, what they do is like basically when the gravitational wave passes by, they change the lengths of everything really, but they can by measuring the relative differences in length in these two big interferometers, they can detect and characterize these events in the sky. So for this to have these gravitational waves, usually we need a very massive, very energetic events in space, usually mergers or big explosions. So binary neutron star, binary black hole mergers, or neutron star black hole mergers, they're all transient events that can be detected on these two observatories. The kilonova are expected, the optical counterpart to this binary neutron star merger, and that's one possible source that we can find in this TOROS observatory. And also, of course, any gravitational wave detection will be enormously more valuable if an optical counterpart can be identified independently. This image in the background is actually you can see this, those two long arms are the interferometers there in the vacuum, and they're like 4 kilometers long. That is LIGO here in the US, one of the two. The problem with these detectors is that they're not that much accurate on where the location of the source is. And this doesn't have to do with the sensitivity of one single detector, but rather how many detectors you have to localize, to triangulate the source. And with the three that we have that we will have functioning soon, or maybe 2016, I think, or 2017, depending. With those three, the sensitivity for a neutron star merger is about the confidence 95 confidence region is like 480 degrees. So TOROS will need to scan through these regions, searching for a good candidate optical counterpart, and the situation gets better if we add more interferometers, and there are already plans to do that. Japan with Kagra, and then India is also planning to have another one. The situation will improve with many more interferometers, but the situation right now is like any localization of the source is going to be pretty hard because it's a very large region of the sky. They expect to have like 50 detectors per year, and median localization area of 250 square degrees. So I was saying that the implication for TOROS is that it definitely will force a large field of view, and that in turn will require more computational power and storage power. On top of that, when another service mode of TOROS, when it's not responding to triggers, will be to survey the southern sky, and this survey will help us when a new image comes to compare against the image on the survey. We plan that we think that we can do that on the first year of operation to survey the southern sky with about like 2,000 pointings. And yeah, and I should say that I think I said it, but the conditions of the site are very good in terms of seeing, so we can probably look very deep with relatively low exposure time. So what about this kilonovae? These are good candidates for both advanced LIGO, advanced Virgo, and TOROS. So we've been doing some simulations. These images are not, the first are not from us, but we've done some simulations on how this kilonova could look like in our telescope, and it's still ongoing. We don't have like a definite answer, but this will help us a lot in understanding how much we can see and what are the best techniques to embed these signals from our data. We basically will be doing image subtraction to reveal those, and then on the image subtraction, then we can test either match filtering or running windows or any other technique to make the signal pop out and be discovered. So in general, the pipeline will have to take care of basically all the operations from taking the image to identify a possible candidate. This means that it will have to do the data reduction steps, device flat fielding, the sensor corrections because it's a wide field, and photometric calibration all in the pipeline. And then do the search for transients, image subtracting, and going through different techniques to try to see if we can get any kilonova or similar, and then classify all the transients we detect. And if we find a good candidate, then the pipeline should decide also whether to do a follow-up and when on the source. So all this will have to be done in a matter of hours, and we have the advantage that we can now decide basically what path are we taking, and we decided we wanted to make this a coherent thing, mostly done in Python as much as we can. And one of the things that the pipeline requires is the image subtraction, that it will this in turn requires a good astrometric solution and then a good PSF estimation. And to give you an example of what we're doing, we have some kind of in-house alignment algorithm that we're using. Basically, right now we're working with a set of images from a Chinese mission to the South Pole called C-Star, and this is our test set to test our pipeline. The way we're doing it now for alignment is cut everything above 3 sigma and use OpenCV to find connected components, and then find the centrist on that. OpenCV, for those of you that don't know, is like a library for robotic vision, and it doesn't have anything to do with astronomy, but we find that at least it gets the job done. And once we identify the stars with this OpenCV, we find the brightest 100, and then with an approximate transformation, we do the matching between the two images, and then we feed that through a ransack algorithm and to pick the best linear transformation between the images that fits the most inliers and that avoids getting noise from the outlier from the wrong matchings. One of the reasons we did this is because the images we are using don't have much information at all in the header. It's just a telescope that points to the South Pole, and it doesn't do any tracking at all. So like stars go in circles, and there really isn't much information in the header other than the time. And even that has to be corrected because it's not actually accurate. So we use this technique to align them all. Then we use astrometry.net, which we find is a pretty good solution. It's even the online version. You upload any image and it will return a fits image with the correct astrometry solution. And then we copy on the rest since they were pretty much all aligned, and that's how we deal with the alignment. On the subtraction, that is where we are starting now. We haven't really done much on this, but we're going to use the Allard-Lapton algorithm, OIS. I think it's optical image subtraction. This technique will correct the two images that are going to be subtracted. They correct the relative PSF and the relative background difference between those two images by optimizing what is the best kernel and background that minimizes the subtraction. So it's an optimization problem, and it's done through least square. And to make it linear, this algorithm proposes to write the kernel as a linear combination of some functions, usually Gaussians for the kernel. These Gaussians are fixed. They're not really a basis for anything, but it's just guesses of the kernel. Then the algorithm will adjust the coefficients on the linear combination to make it to optimize the subtraction. The same can be done with the background. In the background, you need to put some kind of a polynomial basis to a certain degree in x and y, but the idea is the same. The coefficients are pulled all together in a big vector, and this can be optimized really simple. That's code to show you how easy it was to implement this, as opposed to do it, for example, in C or any other language. Actually, at first I tried to do some stuff in C, and then I gave up, and I coded this like in a day. It's really easy. And so for once after the subtraction is done, a lot of things still have to be done. The subtraction will leave behind many transients that we don't really care for, and also things that we do care for will still be buried maybe in noise. So we're not at this stage of we're not at this stage right now, but the things we want to implement is machine learning algorithm or techniques to discriminate between for example, Bugs subtraction artifacts and the many transients that could be on the image. So, well, yeah, I explained this already. The team in Argentina, in Cordoba, they are working on this part of the problem, and with the image, but not on simulations and not in real images. Many of the things that we will find, for example, moving objects, satellite tracks, meteorites, all those things will present a challenge for the image abstraction part, in that they will appear many times, and they won't have a light curve if it's moving, basically, because it will appear at different positions in all images. So for those things, we will have to find some separate way to remove them, and variable stars will also be there after subtraction, and but we can take them out by using some machine learning algorithm on light curves, and then yeah, all kind of stuff. Then lastly, I was going to talk about a little bit. These are some of the packages we used. We of course use SciPy heavily. We use actually phototils. I'm glad that they're going to release a version now, because we are already using it. S-Extractor and OpenCV. We found that it's pretty useful for some stuff, especially image conversions and interpolations. Astrometry.net is a pretty good one for the calibration. We find out. We would like to see implemented site database, which is a kind of database that works on the images directly. It's you store not a catalog, but the image itself, and then access the images as if it were a database. Like, give me this date, this region, and you can work on it. We would really like to have that implemented, but it's not yet done. And of course, Git flow, external repositories, and for machine learning, we will use scikit-learn probably in AstroML. All these packages and many more that I learned about in this conference. So yeah, that's all. Thanks.